Ja, välkomna igen. Välkomna till den här presskonferensen där vi ska presentera årets Nobelpris i kemi. Welcome to this press conference where we'll present this year's Nobel Prize in chemistry. As usual, we will start in Swedish and then continue the presentation in English. When we come to the questions, you're free to pose the question in either of these two languages. Jag heter Staffan Normark, är ständig sekreterare här vid Kungliga Vetenskapsakademin, och med mig som bisittare har jag två sakkunniga kemister. Till höger om mig sitter professor Sven Lidin. Han är ordförande i Nobelkommittén för kemi och han kan svara på frågor kring kommitténs prisarbete och också ge en kort introduktion. Och till vänster om mig har jag professor Gunnar Karlström. Han är ledamot i Nobelkommittén för kemi och han kommer strax att berätta mer om priset. Årets pris handlar om att flytta de kemiska experimenten till cyberrymden. Kungliga Vetenskapsakademin har beslutat utdela 2013 års Nobelpris i kemi till professor Martin Karplus vid Université de Strasbourg, Frankrike, och Harvard University, Cambridge, Massachusetts, USA, och professor Michael Levitt vid Stanford University School of Medicine, Kalifornien, USA, och professor Ari Warshel vid University of Southern California, Los Angeles, USA. Akademins motivering lyder: för utvecklandet av flerskalemodeller för komplexa kemiska system. This year's prize is about taking the chemical experiment to cyberspace. The Royal Swedish Academy of Sciences has decided to award the 2013 Nobel Prize in Chemistry to Professor Martin Karplus at Université de Strasbourg, France, and Harvard University, Cambridge, Massachusetts, USA, and Professor Michael Levitt at Stanford University School of Medicine, California, USA, and Professor Ari Warshel at University of Southern California, Los Angeles, USA. And the Academy citation runs for the development of multi-scale models for complex chemical systems. So please, Professor Lidin, will you give a short summary now in English?
Chemistry is an experimental science, but today theoretical chemists are providing answers to questions concerning complex chemical reactions. Theoretical chemists are working together with experimentalists to help us understand the complex reactions in photosynthesis, how to design drugs to fit with their target molecules in the body, and how a catalyst works in your car or in chemical industry. To model chemical reactions, you can use two completely different sides of physics and chemistry. That is the world of quantum physics and the world of classical physics. Quantum physics allows us to look at chemical reactions in exquisite detail. But it is a method that demands a lot in terms of computer power. And for large complex systems, it is beyond what is possible today and will remain impossible to reach even for the foreseeable future. Classical Newtonian physics, on the other hand, is relatively easy to handle and can be used for very, very large systems indeed. But these models have the drawback that they cannot model the making and breaking of chemical bonds, chemical reactions. The natural way to use the two is together. And so what is needed is a way to find quantum mechanics and classical mechanics to shake hands. As simple as that. Now, actually handshaking isn't all that simple. And the contributions from this year's laureates, Professor Martin Karplus, Professor Michael Levitt, and Professor Ari Warshel, is that they have provided that secret handshake that brings theoretical chemistry together as one unit.
Thank you, Professor Lidin. And now, Professor Gunnar Karlström, are you ready to give a more detailed presentation?
I think it was an excellent presentation Sven did, especially the final end here. I don't know if anything more needs to be said, but I'll try to do something anyway. This year's Nobel Prize laureates, as you can see up here, they've done something extraordinary. They've actually made theory an equal partner to an experiment. For me as a theoretician, this was unthinkable 20 years ago or so. We were always inferior to the experimentalists. They always knew what was right, and we were always saying. We tried to say, but now today, theory is actually an equal partner. And why has that happened? Well, the reason is that today chemistry focuses a lot on function and reactions. And these are issues which are hard for experimentalists to assess. Basically, molecules are lazy creatures. That most of the time they don't do anything. They just swing around and doesn't do anything. And then suddenly, when they react, everything goes quick like that. And that's very hard to study experimentally, because you look at it and nothing happens, and then suddenly everything happens. Theory doesn't suffer from this. Theory controls time, theory controls everything. So we can make things do exactly what we want, and in that way, theory is an excellent complement to the experiment. And what we illustrate here, and I think I should use this one here, we have a theoretician here and we have an experimentalist there. And normally, the experimentalist provides a structure to the theoretician, and the theoretician, he analyzes the structure and he suggests reactions, mechanisms, and so on, gives them back to the experimentalist, who verifies or falsifies and gives back suggestions about new calculations that should be done. And together, they climb the never-ending stairs of chemical knowledge. So what can we do with this type of modeling? Well, I've just given two examples here. Photosynthesis is something which is interesting to everybody. Can we solve the problem of photosynthesis? We have an infinite amount of energy available to us. Or new pharmaceuticals, the docking of a protein with a drug is an extremely important phenomenon. Can we solve these problems in the computer? Then we don't need to do any experiments on rats or monkeys or whatever. Maybe, at least couldn't do fewer. So, what is the problem? Well, the problem is indicated in this little cartoon here. This guy you see here, that's meant to be Isaac Newton, who did his discoveries at the middle or end of the 17th century, and his mechanics. And you see this guy here, this is a cat, Schrödinger's cat, and that one represents quantum mechanics, which grew from 1905 to 1925, and the important names are probably Planck, Bohr, Schrödinger, and Heisenberg. And as you see, they do not fully agree. The problem is, quantum chemistry works with wave functions. Wave functions doesn't allow to calculate position and velocity, position and speed at the same time, because that's the way quantum mechanics is. So you can't really make them work together, not easily. But this year's Nobel Prize laureates, they made it look more like this. They are friends. And the trick which they introduced was they realized that if you treat some degrees of freedom using quantum mechanics and some degrees of freedom using classical mechanics, then it may work if you provide a suitable coupling between the classical and quantum degrees of freedom. So, you can look upon it from in this way, so to say. You have, they devised methods which allowed you to concentrate the attention to the central part, where everything happened. And that was used quantum chemically. And the far away parts was treated using classical mechanics. Just as we have done in this picture here of our laureate, our founder, Alfred Nobel. And you can see the center of his face is clear, many pixels, a lot of computer resources is needed to reproduce that, whereas the far out parts which are less important. I mean, his jacket and so on, that's not very important. Less computer power is spent on that. So exactly the same thing is done here. And you see, we illustrated the quantum physics with a cat and the classical physics with the apple, and that will be the symbols in the future here, and pictures that to come. So, what have they done, these Nobel Prize laureates? Well, they actually sent away a 3-step rocket. The first step was this one, the second is this one now. We'll come back to them now. You see, the first step was taken when Ari Warshel visited Martin Karplus at Harvard in the beginning of the 70s. And together, they devised a method where they described planar molecules, because the thing they did could only be used for planar molecules, to calculate the infrared and the UV spectra of these planar molecules. And the thing which is indicated above here and below that is what chemists call pi electrons. These are electrons which are above and below the plane of the symmetry. And the remaining part is the sigma skeleton, as we say, that is the nuclei and the bonds, the electrons which are in the plane. That was modeled classically, but the pi system was modeled using quantum physics. And they actually made good success in this type of modeling. So this was the first time anybody ever merged a quantum and a classical world in chemistry. A few years later, Warshel and Leavitt wanted to lift this restriction that it only could be used for planar systems. And they used it to study lysozyme. This is, you see the big white thing is the full protein, and this is the yellow part here is the thing which they studied, which is a small part of it, and it has a catalytic effect. And what they did was that they studied the catalytic effect of this protein. And this part here, which is this part here, that was studied quantum chemically, and the remaining, the yellow part, was studied using classical mechanics. And they got insight into the mechanism of this catalyst, this enzyme. But they didn't stop there. They did something more. They coarse-grained they showed that you could make a coarse-grained model where you lump together particles. As you see how what we have here is a protein chain or polypeptide chain. And atoms here were lumped together as indicated by these rings here. So all atoms that were in one ring were modeled as one new particle. And you got a model which looks like this. That was a coarse-grained model. The advantage of this is that you reduce the number of particles. And when you reduce the number of particles, simulations modeling is quicker. So it's all about making the calculations with the minimum needed effort, but getting the maximum possible accuracy. And this, for some type of application, this is a very good model. So what do we gain from this? We gain understanding. Understanding is something which cannot easily be provided by experiment. But from the calculations that we do, we can see why is this reaction proceeding? What is the reason for the reaction barrier? Can we lower the barrier by some technique? Maybe has it an electrostatic origin? Does it require a lot of energy to bring the reactant and the two reacting molecules together? Maybe. Okay, then maybe we could put something which facilitates that, some charged particle which facilitates that. So the immense success of this basically is that it gives us understanding. And with that, I think I should stop here, and hopefully we have some of the laureates on the line.
Well, we got hold of all three laureates, and now I hope that we have Professor Warshel here with us on the phone. It's very early, 3 o'clock or so in Los Angeles. Are you there, Professor Warshel?
Yes.
Congratulations. So how do you feel at this very early morning time for you?
Extremely well.
That's good to hear. I'm sitting here in the session hall of the Royal Swedish Academy of Sciences, and in front of me
I see you.
Oh, you see us as well. Well, we have a lot of persons from the media all over the world, and are you willing to take some questions from them?
Very glad to.
Do we have a question?
Yes.
We start there.
Yes, hello, Professor Warshel. My name is Maria Gunter-Axelsson. I'm writing for Swedish daily newspaper Dagens Nyheter. At first, congratulations to the prize.
Thank you very much.
Yes. And we just had a presentation here of what you have done. And could you just say something that have been easier to understand now that you couldn't understand before you had this?
Yes. Usually I say it in a more complex way, but what we done, from what I was able to see from the presentation of Gunnar, is to develop methods that allow how proteins actually work, because X-ray structure of protein exists for some time, and it's like seeing a watch and wondering how actually it works. So, in short, what we develop is a way which requires a computer to take the structure of a protein and then to eventually understand how exactly it does what it does. Like if you have an enzyme that digests food and the structure exists, you want to understand how this is happening, and then you could use it, for example, to design drugs, or just, like in my case, to satisfy your curiosity.
Okay, thank you. You had a question?
Hello, my name is Joanna Rose. I am writing for a Swedish popular science magazine, Forskning och Framsteg. Congratulations to the prize. I'm curious about what is the work that you're doing now, presently.
I am now using, I saw it in the presentation, on one hand, I continue to use this combined quantum molecular mechanics to understand how proteins that are responsible to transfer signals in the cells, how they exactly work. So this is like 30% of what I am doing. And I also use this simpler representation to understand how molecular motors work, to understand how very complex molecules are working. So it's all the time it's how the things are working, and every time it's for more complex questions.
Okay, thank you very much. Do I see any more questions here? I don't think so. So thank you once again, Professor Warshel, and congratulations. We are looking forward all to see you here in Stockholm in December for the Nobel Prize ceremony. Bye.
Thank you very much, and looking forward.
So now I'm turning to the audience here. Are there any questions you would like to pose to the experts here at the podium? If not, I think we will close this press conference. Thank you very much for your attention, and I hope to see you all back on Monday the 14th at 1 p.m. at that time, and we will announce the Sveriges Riksbank Prize in Economic Sciences in memory of Alfred Nobel. So thank you very much for coming.